So we're now treating light as a wave, and it's worth reminding ourselves of a couple of properties of waves. So waves do something that particles don't. If I have two particles and they show up at the same point in space and time, they collide. Whereas what waves do is they basically just add their individual disturbances, or in the case of an electromagnetic field, amplitudes. And this somewhat grandiosely is called the principle of superposition. So I have, maybe think about water waves for a second. I have one person over here splashing and making this water wave. I have another person over here splashing and making this water wave. And when they come together, I just add the individual disturbances. So in this case, if this was a wave from source 1, and this is a wave from source 2, the total disturbance, and this is one of two phenomena that are really important. The total disturbance I would get from adding them up. So here I've got trough and trough, and here I've got crest and crest. So basically what I would have is twice as much of the individual disturbance in this particular case. So when the waves add in such a way that the minima get more minimum and the maxima increase in size too, maxima meets maximum, minimum meets minimum, this is what we call constructive interference. And if each one of these waves had amplitude, and we won't talk about the amplitudes of electromagnetic waves, and you're going to be happy about that because the amplitudes of electromagnetic waves are pretty tricky to talk about. They're the amplitudes of the electric and magnetic fields. But for instance, if this had an amplitude A and this also had an amplitude A, I would get a total disturbance of amplitude 2A. So that's what constructive interference means. So we could also do this in another way. We could have destructive interference. And how would I get destructive interference? Well, let's say that source 1 was the same, but the person splashing and making the second source, source 2, just splashed a little bit out of sync. So instead of the maxima lining up with the maxima, I have maxima lining up with minima. And that might look something like this. So here, where wave 1 is at its max, wave 2 is at its min. Here, where wave 1 is at its min, wave 2 is at its max. And now when you guys look at this and you see them lining up, what I have is not peak lining up with peak, but peak lining up with trough. And if these things still have amplitude A, so the amplitude would be the distance from the midpoint to the highest point or the lowest point, now what happens when I'm adding them up, which I always do according to the principle of superposition, is min plus max, so this would be minus A plus A really quickly. Well, that equals 0. What about here? Well, that's A plus minus A. That's also 0. Minus A plus A, 0. And you can kind of argue your way through the rest of the wave. Here I have 0 plus 0, 0 plus 0. So in fact, when I add these up, I get no disturbance whatsoever. So this is actually what's called total, because it's all gone, total destructive interference. And as we talked about, this is kind of hard to depict because waves evolve in both space and time. So this would be like one particular snapshot in time of two waves that are totally destructively interfering. And I'll post some videos of water waves destructively and constructively interfering. And what would actually happen is these would evolve in time. So how would I create a scenario where I have such a thing? Well, let's do a simple 1D example. And this is a really, really, really important example because what it's going to do is it's going to provide the general criteria for Young's double-slit experiment and then also for more complicated things like diffraction. So I'll just denote this by S2 as source 2, right? So nothing fancy. And you can think about these, let's just think about these as sound waves. So this is a speaker, literally a speaker. And let me just have a wave coming out of the speaker 2. And the wave could be depicted like this. So this would be a diagrammatic depiction of this would be where the pressure in the sound wave is high, and this would be where the pressure in the sound wave is low. But, it's a wave. So let's say that I put speaker 1 behind speaker 2. And let's say I put speaker 1 exactly 1 wavelength behind speaker 2. So remember, a wavelength is the distance from peak to peak or trough to trough. So 1 wavelength would be that. So for instance, from here to here, trough to trough. And trust my words, not my picture. But what would happen if I did that? I put source 1 behind exactly 1 wavelength behind source 2. Of course, you all shouted out in unison that, well, I would engineer constructive interference because what I have is 1 full wavelength, right? And then now what's going to happen is they're both at the exact same point in their cycles, and when I add them up, I would get twice as much amplitude. Okay? So if this distance is 1 wavelength, I would engineer a situation where I have constructive interference. Okay, so let's say that I'm really bad at sound engineering, and instead, so here we have constructive. How would I engineer destructive interference? So in fact, you guys might have a whole bunch of different answers. So somebody may have said, well, you just put it a half wavelength farther, so 1.5 wavelengths. Somebody may say that, no, I put it a half wavelength closer, so it's a half wavelength away. And I'll just draw that. And it turns out that all of those things are right. And we can come up with a general criteria for constructive versus destructive interference based on whole or half numbers of wavelengths. So now let's say this is exactly 1/2 of a wavelength behind speaker 1. So that's 1 lump. And I'll kind of get the tip of the pen grody by doing this right. So the sound wave from speaker 1 would look like this, and the sound wave from speaker 2, because they're in sync, which I didn't say, but we were assuming, they're both at the same point in their cycle. And now what happens when I add this? I get totally destructive interference, and not the creepy disembodied eye, but the creepy disembodied ear that's out here listening to this would actually hear absolutely nothing if we did this perfectly. So this is destructive. And what you may have realized as we're doing this is that, well, we could have put this 2 wavelengths or 3 wavelengths or 4 wavelengths behind speaker 2. So there is a general criteria for constructive and destructive interference if I have identical sound waves or light waves or any other wave. And you can basically just read it off this argument, and it works in 1D, it works in 2, 3D. If you're a string theorist, it even works in 10D. So the jargony term is in phase. It means that they're basically, the sources are in sync with each other. And that means their frequencies are equal and they're basically oscillating at the same time. So for waves that are in phase, we get this general criteria for constructive interference. And I'll just say delta R for the path length difference. And the path length difference in this case is the distance that each one is to the ear, the observer. So in this case, speaker 2, we'll just call it R2, right? It's whatever that is. And R1 would be R2 plus a half a wavelength. And the path length difference, delta R, would be that 1/2 wavelength. So that's what path length difference means, is the extra distance that one of these two has to travel. So we're constructive if the path length difference is equal to, we'll just say n lambda. And n can be equal to 0, plus 1, minus 1, plus 2, minus 2. Any negative or positive integer at all. So any whole multiple of wavelengths, either shorter or longer, it's what the plus or minus means. So if I get any whole number of wavelengths difference in between them, they're going to show up in sync, and I'm going to get constructive interference. Okay, so scratch your head a little bit. What is the general criteria for destructive interference? So now path length difference, I could be half a wavelength. I could be negative half a wavelength. I could be 3/2 of a wavelength. So in this case, I've got to figure out a way of writing it. There are a couple of different ways. I'll remind myself of what your book uses. So the plus 1/2. So this is an integer, and then what I can do is have any whole number, so any positive or negative integer, and then just add a half. So in this case, m would also be plus or minus 1, plus or minus 2, dot, dot, dot. And this is really it if you have two waves again in phase, so same frequency, same wavelength. Ta-da. So let me do a really quick example with numbers, just so you guys can see how this would work. And then we'll turn this into 2D, which is essentially the smoking gun experimental proof that light really was a wave. And this was done in the year 1800. So so-called Young's double-slit experiment. So let's just say let's keep it with sound. So put one speaker 25 centimeters behind another, and they're both playing the exact same grody sine wave. And it turns out that this problem takes much longer to write than it does to solve. So I'll draw a diagram. I've got two speakers. They're separated by 25 centimeters. So there's S1 and there's S2. And they're both playing sound. And I have total destructive interference, which means that something like this is happening. And what I want is, so the reason to pick this particular problem is it points something out, is the three longest wavelengths. Is that going to correspond to the biggest or the smallest n? So it turns out the bigger that n is, that's going to talk about shorter and shorter wavelengths because we're packing more and more of them into this amount of space. So in fact, the longest wavelength that we can do this, that we can have destructive interference, is actually going to be associated with the exact picture that we drew. So this is the longest wavelength, and I'll draw the next longest, and then I'll run out of the ability to draw them probably. So in this case, what we have is an extra half wavelength. And in this case, again, 25 centimeters. How would I draw this so that I get not 1/2 wavelength, but the next possibility? So that would be 3/2 wavelengths. So I will try to draw 3/2 of a wavelength. That's a full wavelength, and then an extra half. So that's 3 lumps, 2 up, 1 down. And that would end up in this situation. So this is what these numbers correspond to and mean. So essentially, I've got half a wavelength here. So the path length difference, in this case, delta r, which we're told is 25 centimeters, this corresponds to 1/2 of lambda. Okay. So that would make lambda for the largest. This is the largest wavelength we could draw, 50 centimeters. Okay, in this case, the path length difference, delta R, is still 25 centimeters. That's the separation in between the speakers. But now we have 3/2 of a wavelength. That would be what we mean by plus, m equals +1. So that would be 1 plus 1/2 lambda. Or what that means is lambda second longest, so we'll call it second, is 2/3 times 25. Right, whatever that happens to be. And then likewise for the third one, I would get delta R. That would correspond to me packing 2 full wavelengths and then an extra half wavelength in. I'll try to draw that really quickly, but this won't be the best picture. So 2 full wavelengths, 1, 2, and then an extra half. Okay. So this is what these little formula mean. It's just basically counting the number of wavelengths that one has to travel farther than the other. So in this case, delta R is still 25 centimeters for the third longest. So delta R is still 25 centimeters, but then that would be 5/2 lambda, or lambda third would be 2/5 times 25 centimeters, or 10 cm. Okay, so we get 50 cm, we get 10 cm, and then in the middle we get 50/3, which is like 16 and change. Right. Okay, so honestly, those are all of the individual pieces you need to understand this whopping important 2D or 3D experiment. We'll keep it to 2D with slits, and this is what's called Young's double-slit experiment. And I'll post a link to a video of somebody recreating a modern version of it and baffling the general population of Edinburgh. Because it's a little bit non-intuitive, and it's a really difficult experiment to do with actual visible light too, for a reason that I'll ask you guys about, but not hear your answer. So Young's double-slit experiment basically works exactly like it sounds. And the problem with depicting it is that the wavelength of light is so small for visible light that I've just got to give you like a really out-of-whack schematic of this. So basically I have a thing like a playing card, I think was originally used in Young's experiment, or something, a piece of cardboard, and there are 2 slits in it. And what I'm going to do is I'm going to shine light on the back of the slit. And what you'll do in a virtual lab later in the quarter is you'll analyze data for a laser. So the nice thing about a laser is it's just one color, and it's only got one wavelength, and it's a plane wave. So this plane wave comes in, and then I know this weird thing about Haugen's principle, and I know that only one wavelength or one wavelet would come out if I had ideal super teeny tiny double slits, and the next one would be one wavelength over, so it might look like this. Get one that looks like that, and then about this far over, and we'll draw a third one. So basically, I would get diffractive type behavior, right? So plane wave comes in, and then these individual wavelets come back out. And what I can do is, by looking at this, and basically can this drawing really quickly, is these are the wave fronts, right? So this is where the electromagnetic wave, in this case, is at its peak. So I have peak meets peak, and I have peak meets peak, and I have peak meets peak. So basically, where those circles are I have constructive interference. But then I also have locations where I have, in this case, halfway in between the 2 peaks is a trough. So here I get peak meets trough, here I get peak meets trough, here I get peak meets trough, and I could add a couple more. So there would be one like here and here and here. So basically I get these alternating bright spots and dark spots. So there would be destructive. So if you think about projecting this on a screen, what you would imagine seeing is this alternating pattern of bright and dark spots. And you can reason through this, and it makes perfect sense if you're just talking about one particular color, one wavelength of light. One of the problems with Young's experiment is that he didn't really have access to lasers in the year 1800, so he was trying to do this with white light. And if you can't envision it already, you'll see what the pattern looks like in white light. So what you get is this series of double ripples, constructive and destructive interference. This isn't really going to be a helpful diagram because what we'd like to do is use our insight about path length differences. So instead of talking about the wave fronts, we'll just basically repeat this picture and talk about the wave vectors, aka the rays. And the question is, here's a double slit apparatus, so 2 slits, and then here's a screen. And my screen is pretty dang far away, so we'll just call that L is the difference. And these 2 slits are separated by D. Make sure I'm using he uses D, great. And what I want to know is what's going on at this point on the slit, right? So on the screen, sorry. So at this point on the screen, do I have a light spot or a dark spot? Because I know they're going to alternate depending on the particular nature of the peaks and troughs. And remember, these things are also wiggling at maybe 10 to the 15 times per second. So here I've got something coming out of slit, whoops, change my point, out of slit 2, and here I've got something coming out of slit 1, so here's R1 and here's R2. And you can clearly see that if I'm above or below the center point of the screen, if I'm right in the middle of the screen, like directly across from the slit complex, they're going to travel the same path length. I'm going to get constructive interference. However, if I move myself up, it looks like ray 1 has to travel less distance than ray 2, right? So I can make a little triangle and come up with some trigonometry that describes that. There is a big assumption in this, but it's honestly not that crazy. So I'll draw this triangle. And now I have a side D, which is like a hypotenuse, and I have this side. And I'm going to argue that if the length, so this distance to this distance, is much, much bigger than the slit distance. So imagine that this slit is like really teeny tiny, and the screen is 10 feet like back there. So in actual practice, these slits might be the width of, distance of a human hair apart or something like that. And this is, meters. So this is okay. So imagine if this is really far away. Essentially, these 2 rays are parallel. And so in that case, this really does become a right triangle. So I drew it already, but the argument that this really is a right triangle is the argument that it's approximately a right triangle when the slit is really far away compared to the slit spacing. So as such, we got this right triangle. It's got side D. It's got a right side, and it's got this angle theta. And I'll argue that that angle theta is the angle that you lift up off of the midline in a second. And then therefore, this is d sine theta. And that is the path length difference. So that's the important result. So what is this angle theta here? Well, if you look at these 2 sides, so right angles, is that these 2 grow together. So basically, the angle theta is the angle that you are above the midpoint. So directly across from the slit complex, the angle above or below that is theta. That's also the angle that you pull this ray off the side. So what you have is d sine theta equals delta r. And delta r is exactly the thing that we want, because we know all criteria for constructive or destructive interference based on that. So delta r can be, these are the landmarks, and other things that aren't perfectly constructive or destructive are happening in between them. But when delta r is m lambda, we get constructive. And when delta r is m plus 1/2 lambda, we get destructive. And again, m is 0, plus or minus 1, plus or minus 2, dot, 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 dot. But now we know from the geometry of the double slit experiment, in the limit that the screen is much farther apart than the slits, which is a pretty reasonable limit, we know that's d sine theta. So at the end of all of this, you'll end up with a formula that you'll probably just kind of reflexively remember is just d sine theta equals m lambda, and d sine theta equals m plus 1/2 lambda. The other way of writing this, I'll just put it up there just in case you see it online, is d sine theta m plus 2m plus 1 over 2 lambda for the constructive or destructive. So this is something that's like absolutely a wave-like property. So you don't get destructive or constructive interference with billiard balls or particles of any type, or at least classical non-quantum ones. So the fact that there was interference that was observed really is like the hallmark. Yeah, this is light. So why was this tough to see? Well, there are two reasons why it was tough to see. One of the reasons is that white light is a mixture of all different wavelengths. So there's different, if you look at the angle you need to look at, it depends on lambda. And white light has a whole bunch of lambdas. The other reason that it's difficult to see is because just literally the distances involved. I got to have such a tiny d and such a far slit spacing. So you'll see what this actually looks like with white light. And we'll do some example problems. Basically, the example problem trick, or the thing that you run into over and over, is small angle approximation.